Welcome back, welcome back, welcome back. I'm Lisa Blackburn, and this is my YouTube channel about everything I want to talk about science and math. And today we are talking about measurements in chemistry for chemistry class. So if you are taking this as a class, then there is this graphic organizer available on Canvas. If not, you're welcome to, if you like the way I teach this, you're welcome to join us. Okay, now then. So what we're going to learn about is chemical measurements. And I did not get out my copy of the notes. Hey, I think I know them without it. Okay, just sometimes I say things different and I want it to be the same. Okay, let's all cross our fingers that we're going to be able to write on it. So the study of substances and the changes they undergo is chemistry. It's what we're learning. Hey, it's starting off good so far. Let me look here and see if I put the notes here. I had them out earlier. That's what I get for being too organized. I put things away before I'm done with it. Okay. Okay, I think I'm going to have to do that. This is going to make bad TV, but I'm going to have to get out my copy of the notes, because there's more than one way I can say this. And I need to make sure I'm saying it the right way. Haha, I found it easily though. Okay, all right, so. It is different here still. We're gonna leave the second blank. I'm not sure what I wanted there. Systemic approach to solving problems in science. Oh. Y'all don't have that second blank? There you go. I think it's the scientific method. So the scientific method in science, and y'all can just listen to this, is that real science, do you remember how you learned the scientific method in elementary school? Step 1, state your problem. Step 2, like that. Real scientists don't have their little poster on the wall of the scientific method and go, okay, which step am I on? Instead, what they do is they are very systematic in their approach, and they do good science where they only manipulate one variable at a time, and it's used in all scientific study. So they don't really go step by step, but they do define their problem, think of a plan to test it. They only manipulate one variable at a time. They keep good records. They're very careful about how they do everything. But not only that, a lot of things in science have been discovered on accident. So it's not really step 1, step 2. Sometimes it's, oops, I messed up, and then figuring out what you did wrong. Okay, now that we have 2 words for measurement. The first one is qualitative. Which gives the results in a descriptive, non-numeric way. It's what you did when we looked at the candle and the sewer lice. You didn't weigh anything, you didn't measure anything, but you wrote down the color and things like that. So that is a qualitative measurement. What is it called when it has numbers? Quantitative, because it's like that word quantity. Okay, so good measurements. We want to have good measurements. We want to be honest scientists that have good measurements. In science, in research, you can make a lot of money. So sometimes scientists will lie about their numbers to make them look better than they are so that they get more money. Okay, that's the bottom line. And especially in areas where maybe there's a lot more than one variable, like climate change. The climate has lots of variables, doesn't it? The whole world worth of variables. So climate change scientists are notorious for lying about their data and getting caught. So they come out with this shocking study, and then 2 years later, and you read the headline, and it is very shocking. And 2 years later, they got caught. They lied about it. So it makes people skeptical about their data when they keep lying about it. I'm not saying that that there's not climate change. I'm thinking, there's some crazy weather going on out there. Good chance it's true, but that they don't need to lie about their data. They lose their scientific reputation when they do that. Even if your lab doesn't do what you want it to do, we have to resist the temptation to try to manipulate the numbers and make it say what we want it to. So, good measurements tell the truth. So we have different ways of telling whether or not measurements are good or not. The first one is accuracy. Accuracy is how close a measurement comes to the truth. Precision, and sometimes you don't know if you're accurate or not. So instead, a lot of times we look for precision instead. Precision is how closely several measurements come to the same value. Sometimes you don't know if it's true, but if you keep getting the same number, there's a better chance it's true. And then precision is also how finely stated a number is. How many decimal points do you have? How finely stated it is. Okay, so here we've got 3 bullseyes, and here the 3 arrows are all together but not hitting the bullseye. Is it accurate, precise, neither, or both? Which one is it? Is it accurate? No. Is it precise? Yes. So this one is precise, but it's not accurate. It's P, not A. Precise, not accurate. Okay, this one of them hit the bullseye, but they're not together at all. Is it precise? No, it's not precise. And the accuracy is mixed. So it's not precise, mixed accuracy. Okay, how about the last one? Is it accurate? Is it precise? Yes, it's accurate and precise, and that's what we want. That's what we're shooting for it to be accurate and precise. Now, I know I went all the way to the bottom, and some of y'all are having a hard time seeing because I'm scared to roll it. I'm scared if it's going to go up or not. It's all hope. Come on, you can roll. You can roll. Let me write on you. So sometimes if you click several times first, it rolls better. Do you see what it did? So disappointing. So annoying. Okay, we gotta go back over here. Over here. Oh no. We gotta close everything out. Go away. Go away. Okay, it's completely gone. Let's try to go this way. What a pain. So I sent in a help ticket on this to the IT people, and they said it can't be fixed. I'm like, really? You can't, even though it worked before, it can't be fixed. How about if I do this? I don't know if that's going to do that. Hooey. Okay, let's go back here. That kind of worked. Okay, let's see how that does. All right, let's close it out. More fun with sound effects. Open it back up. More fun with sound effects. All right. That's pretty good. All right. Y'all like that better anyway with better handwriting? Okay, this is the deal though. You can't be writing it and not listening to me. Okay? All right, so how we express measurements. There is a thing called scientific notation, and it is a way to write really big or really small numbers. Why do we do this? Yes?
I can't see it like at all.
You can't see it at all now?
No, but can I just move up?
There's no seats. Oh yeah, you can try sitting right there. Let's see if we turn off the overhead and part of the lights, if that helps. Does that help? Yes? A little bit? Well, I'm going to read it to you also. Let's see if we can make it any bigger too. Yeah, that's better. All right. So scientific notation. Why do we have this? One, it's easier than writing lots and lots of zeros. But the other thing is our calculators. Our calculators, our scientific calculators, remember you're supposed to be getting one for this class, and we're going to have a quiz where if you have it, you get 100. If you don't, you get a 0. So get your calculator. But our calculator screens can only show a certain amount of numbers. The calculator can do math on bigger and smaller numbers than it can display. So we need a way to do a shorthand way of doing numbers so we can tell our calculators and our calculators can tell us. Does that make sense to you? Okay, so the format for scientific notation is you have your first number, a decimal, any other non-zero numbers that are significant, that'll make more sense later, times, and normally we don't use X for times anymore. Now that we're in upper math and science, we use a dot or parentheses, right? But this is one instance where we do use a small x for times, and then 10 to an exponent. Okay, good so far? Nobody's crying. This is looking pretty good. Nobody's got a rash. We started talking about numbers. You're handling it very maturely. Very good. Okay, so this is an example one. Here I have this number, 123,000,000,000, and I want to put it in scientific notation. So I take the decimal point, and I see how many frog jumps it is until it gets to its proper place, which is right after the first non-zero number. Since this is not going to leave words anymore, I'm going to go ahead and roll it up for y'all, since we're to here now. Okay, so we're going to count how many places it is here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the number is 1.23 times 10 to the 10th power because we moved 10 jumps. How do we feel about that? You should have learned this already in algebra. I teach this in Algebra 1 when I teach Algebra 1. Did you learn it in Algebra 1? Some of you are saying yes, some of you are saying no. If you didn't, that's okay. Today's a great day to learn it. All right. So let's do another one. Let's look at another one. Okay. So this one has got a bunch of zeros at the beginning. So we're going to count how many places it is to move the decimal. 1, 2, 3, 4, 5, 6. Notice it has to jump over the 1 to get in its proper place. So it's 1.23 times 10 to the negative 6. Very big numbers have positive exponents. Very small numbers that are way less than 1 have negative exponents. Okay, everybody get your calculator out. Let's put some in our calculators. Get out your calculator and let's practice on our calculator. If you don't have your calculator, don't bother with your phone. Just use your calculator because your phone does it different and you're not allowed to use your phone in the test, so we're not even going there. Get out your calculator. If you put your book bag in the cubby and your calculator's in the book bag, go get it. Go get it out of your cubby. All right, so everybody who's got your calculator, look at it, and you're looking for a button that says EE, if you have a TI 82 or 83, it is painted on your calculator behind the comma, which is above the 7. So if you have a TI 82 or 83, look for EE there. Your calculator might say EXP, or it might say times 10 if you have a Casio. Oops, drop it on the floor. It's because it had 2 cases on it. It confused me. Okay, with this calculator, the 36 is right there. It's just 7, and then the fraction button, and then the sign button. It's sign, not sin. Had a kid come up to me once saying, Miss Blackburn, I have proof math is evil. There's a button on the calculator that says sin and sign. Okay, and then above that is EE. Okay, has everybody found it on your calculator? Anybody not found it? Okay, so what you do, so if we were going to put in, so you're looking for EE, EXP, SCI, or times 10. On the TI-84, it's, how you get to it is you do second comma. So the second button is right here, and then you push the comma. And that's how you get to the painted on things. Any questions about that? Okay. All right, so this one, we're going to put it in our calculator. It's 1.6, so everybody turn on your calculator. Okay, clear it out. And then put, if you have this kind of calculator, or whatever you have, see if you can put it in, 1.6, and then push your EE button. Mine, I'm going to do second comma, and it's going to put a little E on there when I do second comma. Okay, and then I do -4. So I push the negative down here and then 4, and it looks like this, 1.6 E -4. That's the same thing as 0.0016, which is the same thing as 1.6 times 10 to the -4th. Now, a couple of things here. You do not push times and you do not push 10. EE or EXP or whatever these buttons are means times 10. Does everybody understand that? You don't push the exponent button. It knows you're putting in an exponent, and it puts that exponent down in numerator land, I call it. I say there's numerator land, exponent land, denominator land. It puts in exponent land. Did y'all ever do that in math class in elementary school where it was a little house, and there's the basement, the main floor, and the attic? They teach that some in elementary school, but I just call it denominator land, numerator land, exponent land. Okay, did everybody manage to get that on your calculator? Yes? Okay, good. Now, some of you are thinking, well, I'm just going to put it in my calculator this way, 1.6 times 10 to the -4th. Don't do it. I know it's tempting, but it will give you the wrong answer often. The reason why is because if you put it in the right way, 1.6 E -4th, your calculator knows that's one number. If you put it in this way, the calculator sees 2 numbers, 1.6 and 10 to the -4th. And your calculator gets confused and will separate it with what's in numerator land and what's in denominator land and what's in exponent land, and you'll get the wrong answer. Does everybody understand? So don't do times 10 exponent like that. You will get the wrong answer, I promise you. All right, so now let's try this one. Try to put in this number. Let me scroll up, and I'll show it to you. Okay, so first of all, let me show you how we got here. So my decimal point's here, 1, 2, 3, 4. This number's more than 1, so it's a positive exponent, 3.6 times 10 to the 4th. Now put it in your calculator. Everybody give it a try. Clear that out and try 3.6. Now if you don't have your calculator, when you get home, you need to try these. Because it's one level of skill to watch me do it. It's a whole different level of skill for you to do it. Put it in your calculator and then hit equals. A lot of your calculators will take it out of scientific notation. Did it do it for you? So on the test, there'll be questions where you have to put it in scientific notation and take it out of scientific notation. If your calculator will do it for you, that's nice, isn't it? There used to be an old calculator, the TI-25, it was before the 36, and it would do it both ways for you. It was the best calculator for this test. Okay, so now try this one. 200, 1, 2 is 2 EE, and then what power should that one have? How many times do we move the decimal place? 2. So this should be times 10 to the second power. So try to put that one in, hit enter, and see if it gives you 200 back again. I didn't want to give you all the answers, so I left that one off. Okay, now let's try to multiply them. You put your two numbers in, put them in again, and multiply them and see if you get 7.2 times 10 to the 5th. Everybody who's got your calculator, try it and see if you can get 7.2 times 10 to the 5th. If you put in the first one and then you just hit times, you don't have to put it in again. It'll say answer times. And then you could do 2 EE to enter. And you might get 7200000 with 5 zeros. Yep, got it? Getting some good math? Okay, so now try this little one. You move the decimal point over 1, 2, 3, 4, 5, 6, 7 times. So it's 3.3 times 10 to the negative 7th. The negative button on this calculator is on the bottom. Negative is not the same thing as minus. Don't do minus, do negative. So give that one a try. See if you can put it in. 3.3 times 10 to the negative 7th, and then say equals, and see if it takes it out. Nope, it left it in there for me. It didn't undo it. Did it undo it for any of y'all? Or did it leave it in scientific? Okay, and then here's 4. 1, 2, 3 places. 4 times 10 to the negative 3rd. Put those two in your calculator. And this time I want you to divide them and see if you get 8.25 times 10 to the negative 5th. Don't you feel smart doing this fancy math? We're doing fancy math. Did you get it? Did you try it and did you get it? 3.3 times 10 to the 7th divided by 4 times 10 to the negative 3rd, 8.25 times 10 to the 5th. Are we good? Can we go on? Some of y'all are still writing, still trying. All right. So the next problem, and you've thought of this problem yourself. You've gotten an answer on your calculator before, and it gives you numbers all the way across the screen. And so you ask your teacher, how many of these should I write down? Right? You've had this problem, right? What do I round to? You've asked your teacher. And your teacher will say 1 decimal point or 2 decimal points. Well, in science, there's rules about how far to round. And it's called significant figures or significant digits. But you know we're nerds in science. And so we like little nicknames for things. So we call them sig figs or sig digs. Okay, it's nerdy, but you know you're part of the community now. So embrace your nerdiness, okay? Sig figs or sig digs. And it's how far to round. And the reason why there's rules about it is that you don't want your numbers to look better than they are. And say that you used a cheap balance and you got that you were doing something where you had to divide the numbers, like you were calculating for density. And you got that it was 2 grams and that it was 3 milliliters. And if you put that into your calculator, it would give you 0.6666666 all the way across the screen, wouldn't it? And if you wrote down all those sixes, it would look like you used a balance at Georgia Tech. and you measured this at Georgia Tech or MIT or one of those places, it would not look like you measured it in room 803 of East Paulding High School. Does that make sense? We have cheap stuff. We do, if something is just measuring to the gram, that's not an expensive balance. Now, we have a few more expensive balances, but if you were just measuring it to gram, that's not expensive. So we can't make our data look like it's better than it is, looking like we used more expensive equipment than we did. That would be lying. Does that make sense to you? It's lying about how much money you spent on your lab equipment. Okay, so now first of all, we need to know how to round. This goes back to elementary school, but you might have learned it wrong. Okay, 5 and up, round up. So if you had 2.5, you could round that up to 3. If you had 2.4, it would stay 2. Everybody good with that rule? Okay, that's the first one. Now there used to be other rules in chemistry that I won't bother teaching you, but there was more to it than 5 and up, round up. The next rule is you only look at the digit next to it to decide to round or not. And there are people, especially if you were private schooled or homeschooled, that have learned this wrong. There's a curriculum called ABECA, I don't know if you've ever heard of it, that teaches this wrong. The way ABECA teaches it is if you have a great big number, I'm going to write one over here, 7.2576128. Okay, great big number. The way they teach it wrong is they say you start at, if I wanted to see what to round this to, I would start way down here at 8. And I would say 8 rounds the 2 up to 3, 3 leaves the 1 alone, 1 leaves the 6 alone, 6 rounds the 7 up, 7 rounds the 5 up to 6. Then you start down here. No. You only look at the digit next to it. None of that matters. The reason why is these numbers way down here are too little to have any effect on this one. Does that make sense to you? And were any of y'all taught that wrong? One time I was tutoring in the library and I was teaching a kid and I said, you might have been taught this wrong. And I was sitting there at the Dallas Library at the table where the young adult fiction is, teaching this kid, and this other kid poked their head through the books and said, I learned it wrong. I learned it that way. They were lurking and learning a little math. They were sneaking to learn a little math. So, gotta watch. So I always want to say that because I don't know if you've been, a lot of private schools use ABECA and they teach this wrong. So if you've been to a private school, you might have learned that wrong. Okay. Now, also, why do we want this? We want to be honest scientists and not make our data look better than it really is. So how you do this is you do the math using all the digits you have. You don't round till your final answer. Everybody got that? Use every number you have all the way through to your final answer. Now, there are 2 different rules and for adding and subtracting and multiplying and dividing. For adding and subtraction, let's say that again. For adding and subtracting, you round your answer to the same number of decimal places, and it shouldn't say and, it should say as the number with the least decimal places. So you look at all of your stuff when you add and subtract, whichever one has the least decimal places, that's your weakest number, and you cannot report your answer any stronger than your weakest number. Any questions about that one? If adding, subtracting, you go with the one that has the least number of decimal places. Got it? But it's different with multiplication and division. Multiplication and division, you round your answer so that your answer has the same number of significant figures as your number with the least number of significant figures. And you must follow the rules. I know that just sounded like gobbledygook to you. Let me explain what it is. We're going to learn how to look at numbers and see how many significant figures there are, how many measured figures there are. If they are significant, we actually measured them. They're not just added as 0 placeholders. Remember when you were in elementary school and you learned how to augment zeros? Do you remember those words? Those zeros that you add in, those would not be significant. Those were just added so that you could do the math. So we only count the numbers that have been measured, okay? So we have to be able to look at a number and tell how many of the numbers were measured, how many of the numbers were significant, okay? It'll make more sense once you do it. I'm seeing some little panicky looks and some eyes here, but it's all right. All right, so these are the rules. All non-zero digits are significant. Any number but 0 counts. It was measured. It had to come from somewhere. If you write down a number, you got it from somewhere, right? So in the number 123.45, it has 5 numbers that are not 0, so they all count, and so this number has 5 significant figures. Are we good so far? Next rule. Zeros between non-zero digits are significant. So if a 0 is between 2 numbers that are not 0, like that 0 is between a 1 and 2, then it counts. It was measured. It's significant. So it was not augmented. So this one has 3 significant figures. Good? Okay, let's do our next one. Zeros that start a number with a decimal are not significant. They're augmented zeros. They were just added so that you know what place this number is in. They're placeholders. So this one, that 0 doesn't count. That one. Zeros at the beginning don't count. So it has 1 significant figure. All right? Okay, next. Zeros at the end of a number after a decimal are significant. So 21.3000, zeros at the end after a decimal count. They were measured. So it has 6 significant figures. Zeros at the beginning, don't count. Zeros at the end, count if they're after a decimal. Good so far? Next one. Zeros at the end of a number with no decimal are not significant. See how there's no decimal there? That means those zeros were not counted. Those were not measured. And so 42 has 2 significant figures. Now there is one thing you'll see even on some worksheets. Sometimes they want to show that 0 was counted and the last one wasn't. So sometimes they will draw a bar over the 0 that counts. So if there is a bar over that 0, it would be 3. It's that same bar that you put, remember, like if you want to show in math that it's 3 that keeps going forever, if you do 1 divided by 3 and you want to show that 0.333 goes forever, you can put a little bar over the 3 and it means it keeps going. It's that same little bar, but what it means here is that 0 was measured. Okay, everybody good with that idea? All right, don't worry. Once you practice it, it will be easy. Okay, so we're going to practice this. Okay, next, change between measurements. Okay, so the next idea is called dimensional analysis or factor label. It's the same thing. And it's how you change between measurements. So in math, you have certain conversion factors, and mathematically they equal 1 because anything divided by itself is 1, right? 5 divided by 5 is 1. 1,000,000 divided by 1,000,000 is 1, right? So if 2 things are equal and they're divided, they equal 1. So 7 days and 1 week is the same thing. So 7 days divided by 1 week mathematically equals 1. Good with that idea? Anything times 1 is itself. 5 times 1 is 5. 1,000,000 times 1 is 1,000,000, right? So if I multiply something by 1, I don't change its value. Does that make sense to you? All right. So if we want to figure out how many seconds it is until winter break, then we could do that. We could figure it out using this method called dimensional analysis. Now I'm going to do this on the board, and it's going to be boring for the people in the video. But people in the video, you can go watch the other video where I was able to write on the board. Okay, so just go find it and fast forward to it. All right, so how many days is it till winter break? Somebody look and see. Isn't it that week? We're here, so it's a week. It's 7 days, I would say. Well, no, I'd say it's less. Well, because we want to know, once it's Friday, we think it's winter break, right? So that's 1 week, that's 7, okay, now that's 7, 8, 9, 10, 11. 11 days. It's 11 days till winter break. So, 11 days. And I want to know how many seconds that is. Well, I don't know how many seconds are in 11 days off the top of my head. But I do know how many hours are in a day. What's that? 24. So what I do is I take whatever unit is here in the denominator and I shove it to in the numerator, I shove it to the denominator. And it's more fun if you do it with sound effects. So I put day down here because I want to be able to mark them out. And whenever you have the same thing in the numerator and denominator, you can cross them out. Good? Okay. All right. So I know that there are 24 hours in one day. They are equivalent. They're equal to 1. And if I multiply them times my days, then I have not changed the value. But I didn't ask how many hours it was till break. I asked how many seconds it was. So I don't know that, but I can say that 1 hour is 60 seconds. Well, no, it's 60 minutes. I'm getting ahead of myself. I'm thinking, oh, we're done. Right? So I can mark out hours, and now I can say that 1 minute is 60 seconds. I mark out minutes, and I'm left with the unit 60 seconds, or the unit of seconds. So everything in the numerator, you multiply. Anything in the denominator, you divide. So in your calculator, you do 11 times 24 times 60 equals, or enter, divided by 1, enter, divided by 1, enter, divided by 1. But anything multiplied or divided by 1 is that thing. So you can skip that. So what's the answer? Did anybody get it? Somebody do it on their calculator for us. Tell us what it is, so we can know how many seconds it is till winter break. Anybody going snow skiing? Not me. No. Anybody got the right answer? What is it?
950,400.
950,400. Is that it? Okay, so when you get an answer in math, I want you to put a box around it. I want you to have a number and units. A number without units is meaningless in science. And I make you put a box around it because, you know, I used to teach those bad kids in Cobb County, and they would cheat by doing a problem every single way they could. And then does that make sense to you? Do you understand the cheating method? They're not sure if they're supposed to add, subtract, multiply, or divide the numbers, so they would do all 4. And then when I would mark it wrong, they'd say, but the right answer was here, but they didn't know how to get the right answer. So it's like, who wants to be a millionaire? Is that your final answer? You have to put a box around your final answer. And it makes it faster for me to grade it, too, if I'm just looking at the answers. All right, so here's another one you could try. How many centimeters are in 4 feet? There's 2.54 centimeters in an inch. So you would write 4 feet on top. And we don't know how many centimeters are in 4 feet, but we do know how many inches are in a foot. Do you know that? Anybody? This is a little thing from that Abeka curriculum. It's a little rhyme. Stop, kaput, 12 inches in a foot. Anybody learn that when you were little? Stop, kaput, 12 inches in a foot. So there's 12 inches in a foot. So you put 4 feet, and then you put 1 foot is 12 inches, and then you put 1 inch on bottom, and an inch is 2.54 centimeters. So I'll let you try that one. I'll tell you the answer for it later. But see if you can figure that one out yourself. Okay, international measurements. Doing good. Moving right along. Okay, also, let me show you something that I noticed as I scrolled by. When you set up these problems, sometimes you will see them set up as fractions with parentheses. I don't want you to do that because I've taught for decades. We don't talk about how many. And the students will write so messy that their parentheses will turn into sixes and they'll get the wrong answer. But with the train tracks, it keeps it neater. Things on the top are in the numerator, things on the bottom are in the denominator. Okay, now we use measurements that can be understood all over the world. My oldest son is getting the chemistry doctorate program. He's getting a doctorate in chemistry from Georgia Tech, and he watches videos from all over the world of people doing chemistry not speaking English. He watches people in China, people in India, they're speaking Punjabi, and he can understand them because he doesn't need to understand their words, because he can understand the elements they're using off of the periodic table, and he can understand their math, and he doesn't need a translator to learn what they're talking about or to understand it. So we have to use certain things so people can understand us all over the world. And it is called Le Système International de Units. I'm sure I said that in perfect French. Or SI. We'll call it SI. It's also called the metric system. They're slightly different, but they're almost the same. And we'll use a little bit of both. And what we use in America, in addition, is the English system. So centimeters is metric, inches is English. When I grew up, I grew up with English, and then they told us, when I was a kid in the 70s, that we were going metric. And I was like, great. And so we started learning metric, and the English was the normal thing, metric was weird, and we could keep them straight. But you have grown up with both, and I think you're the worst at measurement of any generation. You have grown up with liters and gallons. You've grown up with them all mixed, and so you don't have the normal and weird. You just have it all together, and it's the worst. So y'all need to make me, when you grow up, vote for me. I'll be queen of math and science in America, because it'll be a appointed for life position. And I'm going to fix it. I'm going to make it where we use English for everyday things, because it's really more convenient. Miles, cups, teaspoons for cooking. It's a more convenient unit. And we'll use metric for science. But to have you using both systems mixed together makes no sense, and y'all are the worst at measurements of any generation. Sorry, we just had to get real there. So I'm running for Queen of Math and Science. Okay, so how the metric system works is you have certain base units. Length is the meter with the symbol M. Mass is gram with a little g. Time is second. Current is ampere. That might be a new one for you, but you've heard of amps, haven't you? In your stereo system, you need an amp that turns it up. So ampere is for current. Temperature in SI is Kelvin. In metric, it's Celsius, and we're going to use both in this class. We're going to use Kelvin and Celsius. Volume is liter or cubic meter. Also, you need to memorize, it is on the test, that 1 cubic centimeter is the same thing as 1 milliliter. So that's on the test. Put a little star next to that and make sure you learn it. Energy is in joule. You'll use that more in physics next semester, but we will use it a little bit in here. Pressure has a whole bunch of different units. 3 of them, there's more, is pascals, millimeters of mercury, and atmospheres. And I left off the symbol for Pascal because I couldn't remember if it was big P or little p. I think it's big P. But if you want to leave that blank for now, you can, and I'll look it up. Okay? Now, why do we like the metric system in science? Because it's easier to do unit conversion. Unit conversion, you don't have to do the train tracks. Instead, you can change between units easier by moving the decimal place. Mercury's symbol is Hg on the periodic table, so that's where that comes from. Atmosphere, ATM. And we'll get to those again when we do the gas laws. We're going to do some gas chemistry. want you, for homework, I'm going to pass this out. And I want you, we're going to keep with these notes, but while I'm thinking about it, I think you need to practice significant digit sum. So this is a two-sided worksheet. I want you to just do the front side that has the rules on it, that says significant figures. So take one of these and pass it for your homework tonight. I want you to practice this sum while it's in your head. If you wait till Wednesday to practice it, you're not going to remember how to do it. So take one and pass it, and I'll pick the extras up. Okay, so take one of those worksheets, math worksheets, and practice it for tonight. Okay, let's go on with this. Now, can I scroll? We good? All right. So why do we like the metric system? And it's this. It's easier. So here's our little pneumatic device to remember it. It's King Henry's daughter. So everybody imagine King Henry. Imagine his daughter, the princess, bakes delicious chocolate muffins. There's the muffins. Okay, everybody got that? King Henry's daughter bakes delicious chocolate muffins. It stands for kilo, hecto, deca, basic, deci, centi, milli. You can remember that this D is deca, big D is deca, and little d is deci, because deci goes with its E brethren, centi and milli. Good with that idea? Okay, so if we wanted to change 4,800 kilometers to millimeters, then we move the decimal place from K to M, and we count how many frog hops. So this is the story of Princess and the Frog, and the frog is the prince, okay? So we got Princess and the Frog, my favorite Disney movie, my favorite Disney princess movie. Okay, so we're going to go from kilometers to millimeters. We go up here, and we count how many frog hops it is. 1, 2, 3, 4, 5, 6. So we take the decimal point that is right there, stop that is right here at the fourth place, and we're going to hop 6 places in the same direction. We went to the right, so we're going to go to the right. 1, 2, 3, 4, 5, 6. Our new decimal place goes here, and we write zeros for each of the frog hops. Let me do it over here to show you again without it already being written on. That's why it's no good that my board is not working. I'm going to get rid of all that. More fun with sound effects. Okay, so let's do it again. King Henry's daughter bakes delicious chocolate muffins. I have 4,800 kilometers, and I'm going to millimeters, so I count the frog hops. 1, 2, 3, 4, 5, 6. My decimal point is the frog. There he is. He's going to hop 6 places that way. 1, 2, 3, 4, 5, 6. Now he's here, and we put zeros in each of the hoppy places. What do you think? Can you hop like a frog? Okay. So now 6 liters to centiliters. Liter basic is meter or liter or degrees Celsius. Basic is the metric unit. So I am going from liters, the basic, to centiliters. Let's get a different color. We'll do blue. So this time I'm going from basic to centi. It's 2 frog hops that way. So I had 6. I do 2 frog hops, 1, 2. I add the zeros, and it's 600 centiliters. How do you feel about that? Okay, so now try by yourself and then look at the answer. Try to go 679,000 milligrams to decagrams. See if it makes sense. Try it and then look up at the answer. Do you see how much easier this is than the train tracks? No math needed. You just frog hop it. Okay, I'm going to scroll up while y'all give that one a try. Did you get it? 67.9. Got it? Okay, so let's look. I'll do this one. We'll do this one orange. This time I'm going M to D. So I'm going M, this is almost dying. 1, 2, 3 to D. So I'm going decimal points here is 1, 2, 3, 4 frog hops. So you go here, 1, 2, 3, 4, 67.9. Okay, so we have to have some actual something to measure if we're learning about measuring. So we're going to measure density. Density is a physical property of a substance, and mathematically it equals mass over volume. Do you see how I wrote a slash for divide? I did that because Word is not chemistry savvy. I don't want you to do that. I want you to always make flat fraction bars, no slashes unless it's units. The reason why is I've taught for a long time, and people will start with 6 over 2, and in just a minute, that's 612, and they've got the wrong answer. Okay, so I want flat fraction bars, 6 over 2. It will help you get more right answers. Okay, so how do you do a problem? What is the density of a piece of lead that has a mass of 114 grams and a volume of 10 milliliters? So how you do a problem is you list your knowns and unknowns, you think of a formula, you sing a song, and then you do the math. Let me show you how I do the density problem. I think there's some density problems on your practice sheet too for your homework tonight. Okay, we'll use blue. Okay, so first of all, you list your knowns and unknowns. What is the density? So I know density is my unknown. You need to know what you don't know so you can get the answer. Has a mass of 114 grams. So I put mass equals 114 grams and a volume of 10 milliliters. Okay, so in science, usually the problems are word problems. What makes a word problem hard? Is it the math or the words? It's the words. If you get rid of all that words, then it's just easy math and you do it on your calculator. So what makes word problems hard is the words, so we want to get rid of the words. So now we've got rid of the words. This is much better. Now we think of a formula. The formula is density equals mass over volume. Okay? Now, I want you to set it up like this. I want unknowns and unknowns to the right, formula next, and then you're going to substitute into the formula. Now, once you think of the formula, you sing a song. It's before my time, so it's before your time. But if you will sing, and you'll do the dances, and you'll do the hand motions, it will hook it in your memory, and you're going to do better. So yes, can you do math without singing and dancing? I guess, but you're not having as much fun. So this is the song. And yes, I'm a bad singer. That's all right. It goes like this. Substitute is from The Who. It's from the 60s. I told you before my time. Okay, so we sing the song, and we're going to substitute it in. D, we don't know what it is, so it's our variable. So we're going to keep it as a letter. Mass is 114. So right under mass, we write 114. Volume is 10. Now we do the math. So this is 11.4 grams per milliliter, and we box the answer. That's easy math, isn't it? Now, I am adamant about this, and I'm having a big disagreement with it with the physics teachers, but when I teach physics, chemistry, whatever, I say you don't manipulate the formula. If we were looking for volume, you keep the formula the same, you substitute in density and mass, and then you solve for volume. The reason why I'm adamant about that is because I don't just teach chemistry, I teach physics, biology, math, and I know formulas for all of these. And if you write down the formula always the same way without manipulating it, you'll end up memorizing it. I've memorized hundreds, if not thousands, of formulas. But if I moved it around, that wouldn't be one formula, it'd be 3. And I would end up not memorizing them. But Mr. Myrick and Miss Raymond think I'm dead wrong on this. But they only teach physics. They don't teach all the rest, the math and the chemistry. I don't think they're seeing the big picture, but I guess I just have to live and let live, let them do it their way. Okay, the next idea is moles, and we only have a second for this one. Let's see how far we can get. It'd be nice if we could finish it. It's an easy concept. Okay, so you buy eggs in dozens, don't you? And that's 12, right? You buy socks in pairs, and that's 2, but it's also a couple. So the number 12 has another name called dozen. The number 2 has 2 other names, pair and couple. Does that make sense to you? That numbers can have names? Well, what we use for chemicals, you don't go get chemicals in a dozen or in a pair. You get them in a unit called moles. So mole is a little furry animal. So I put one on my wall over there. Isn't he cute? I drew him and stuck him up there this morning to help you remember this. But this number that you get chemicals in has 3 names, just like 2. It's called a mole. It's also called Avogadro's number, named after the guy who invented it, Amadeo Avogadro. That's his picture, and that really looks a lot like him. He wasn't real pretty. He was a good scientist, not a model. Okay, and it's also it's equivalent to 6.02 times 10 to the 23rd. So we are going to do converting with this. Where you get it from, the number is the molar mass, which is the decimal number on the periodic table. Look at the periodic table. Do you see that red little decimal number underneath the elements? Those are the molar masses. We add them up to get the number of moles of something. We abbreviate it MM, molar mass. And do you see the M&Ms I stuck on the periodic table this morning? We're going to use the candy M&M to help us remember how to do these. And we'll get to eat some M&Ms later. Okay. All right, so we're going to stop right there so you got a minute to pack up. If you did not get a lab group written down, I want you to come up to my desk real quick. Like, share, subscribe. Science is great.